So we are jumping over chapter 15 because it seemed to me I don't like to talk about the same thing twice in two different courses, so we're just skipping over group theory. And plus computers are so dang powerful now that I don't think they really even take that much advantage of this stuff anymore. They don't really need to cheat that much. Everything can be ab initio. What was ab initio?
No.
Well, not with a fast computer.
Oh, okay.
They don't, no fudge factors, none whatsoever. Calculate it pure. Okay, so if they can do that, why mess with group theory? Anyway, I don't want to. So let's go ahead and get started here. So you may or may not have read this. Some of it hopefully will remind you of instrumental analysis. Okay. We'll start with section 16.1 here, experimental techniques. So we've got the electromagnetic spectrum. Okay, how about if I do this? What am I drawing? Remember, we're talking about spectroscopy. I'm drawing a wave, right? But this is how the book, I mean, is there any in here? There's some right there. See, they're drawing them. What is that? Yeah, it's a wave. Yeah, but what is it specifically? I was going to Google this, but I had that stupid meeting.
Light.
It's light. Now, light is composed of what?
Photons.
Yeah, well, okay. Now, remember, if I draw this, light's not acting like a photon. It's acting like a wave, right? Now, if we say the word photon, it's acting like a particle. And then you're supposed to write the equation E equals h nu, right? All right, so that's, I think it's all the same stuff. But it still doesn't answer the question. What is this thing?
The transverse wave?
Okay, and we're getting there. Light is a transverse wave. What does that mean? That means this wave, something, this is light. You're right, this is light. Which direction is this wave going? The way it's drawn. It's either going to the right or to the left. It's definitely not going towards you or into the paper because it's a transverse wave. What did that mean? A wave is movement through space. This movement is what, in comparison to the direction the wave's actually propagating through the medium. It's actually going right from the projector, from the bulb to the screen. Right? There's a direction of it. So that's the direction of the wave, but the wave itself is moving, and that movement is in the same direction as it's going, or is it perpendicular? Perpendicular. That's what transverse is. You have this movement. In fact, we can draw it, and they're always lazy. It's just like in general chemistry when we have ions, we never write little AQ on there. Everything, you can't have an ion without it being, soluble, without it being solvated. It's impossible. So you're always supposed to write AQ. Well, here, we should always be writing this movement. It's going up and down. Right? What's going up and down? Even though the wave is all going in this direction. It's transverse. It's propagating. Let's just say it's going to the right. Right? But all the movement is perpendicular to it. What's moving? What is light composed of? All light. Light you can see, light you can't see. All light is composed of what? That's half of it. Magnets, magnetic fields, that's half of it. E equals, let's back up a little bit. Matter, E equals mc squared. You've heard of that. There's t-shirts. What does that mean? E equals, forget about the c squared. E equals m. That means mass equals energy. And the c squared?
Light.
And it's the what of light?
Speed of light.
Speed of light. Okay, you square. Is the speed of light a big number or a small number?
Big number.
It's huge. Square a huge number. You get a huger number. So huger number times a little tiny, tiny bit of mass, you get a whole heck of a lot of what?
Energy.
Energy. So when you say, that's why I had to go through that story, because energy is mass, mass is energy. But no. What is light composed of? And the answer is not mass. Even though mass is energy, energy is mass, and you're getting into some philosophical argument, that's not where I'm headed. What is light composed of? Half of it is a what field? Magnetic field. The other half is electric field, right? Oscillating electric and magnetic fields. Pretty much every time they draw this, they are drawing the what part of light? It's what field? Electric field. And what are they leaving out? They're leaving out the three-dimensionality of it, that it's actually oscillating. So it's actually going from down there to up to there. It's actually going from there, right? They're leaving that part out. So I'm going to leave it out too. Just like I'm too dang lazy to write AQ on every single ion I write in my life. It has to. It has to be oscillating up and down. And it's going this way. And we're interested in the electric field, because the electric field can push electrons around. Electrons can push electric fields around. Electric fields can change the amplitude of the electron moving around. They can interact. Okay? Make sense? Okay. Not all forms of spectroscopy are interested in the electric field. This is a reminder. Which one wasn't? And we have this instrument. It's all about the magnetic field. NMR. Yeah. I should have little fingers. Okay. So, electromagnetic spectrum, our first figure, figure 16.1. You should definitely know this. In fact, you should already know it by having had instrumental. Now you have your cheat sheet here. Mel, which region of the electromagnetic spectrum is involved with Fourier transform infrared spectroscopy? What's the name of it? IR, infrared, right? Okay, according to this thing, infrared's not even a choice. You have to say far infrared or near infrared, right? According to this thing?
Oh, yeah.
Right, that's fine. It's all infrared, though. What is the type of motion that's interacting with infrared radiation in a molecule? Because spectroscopy is all the interaction between what and what? Light and matter. Ooh, there's a point. You remember something? From 2 weeks ago, you better remember. What is the motion in that matter, according to this thing, Jeffrey? Vibration of what? The molecule. Molecule vibrating. They also call them internal modes, by the way. So it's just more jargon to get used to. Internal modes. Okay. We've got rotational motion. Rotational motion of what? Alyssa, rotational motion of what? What's rotating? No. What's rotating? Because back up. What's vibrating? The molecule. So what's rotating? The molecule. Molecule's rotating. So if you want molecules, if you want water, Gloriana, to, I gotta think of a nickname, but I haven't never thought of one.
They call me G.
You want that G. I don't know. That's be something you don't like. Your middle name, like Jeffrey, he hates Jeffrey.
I don't have a middle name.
Anna.
Isn't that your wife's name?
Yeah, that ain't gonna work. All right, Gloriana. You want water molecules to spin faster. You better apply what region of electromagnetic spectrum?
If I want them to spin faster?
The answer's in that chart.
If I want them to spin faster. vibration, right?
That's vibrating. I didn't say, well, I don't want my water to vibrate. I want it to rotate.
Rotation.
So what region of electromagnetic spectrum?
Microwave.
Microwave. So you put it in a microwave oven, right? Hey, this is what I always thought was really interesting. What is higher in energy? You want to heat it up, right? You want to heat up that hot dog, right, Kevin? Mm-hmm. So you throw it in a microwave oven. What's higher in energy, microwaves or? Back up even further. What is the layman's term for infrared radiation? Guy off the street never uses the word infrared radiation. He always uses the word what? Starts with an H. Heat. Yeah, he wants to heat it up. Okay, so Mel, what's higher in energy? Microwaves or infrared radiation? Heat. But we just put our hot dog in a microwave oven to make it hotter. How the hell does that work?
Exciting the water molecule.
The wavelengths are shorter.
Wavelengths are shorter for which one? Heat or microwaves?
Microwaves. Oh no, the IR ones.
IR, because IR is higher energy. So how can we, that's what I'm getting at. How can you put your hot dog in a microwave and it comes out at higher energy level?
The heat from rotating a molecule?
Yeah, what is heat? You're getting there. What is heat? Heat? Yeah, an adjective in front of energy.
Thermal energy?
Yeah, it's too
Potential?
more conceptual. Chaotic. Random. You get all these, give molecules some energy, man. Yeah, it's low energy. It's just rotating. Who really cares? But once you increase their motion, right, get that motion to be more chaotic. Get more of it. You're increasing the temperature. So that's how it does it. Takes a heck of a lot of microwaves is all. Right? Takes a lot of microwaves to get that to work. And it does. That's why you got all this shielding and stuff on there. And that's why you don't want to take that shield off. You'll fry your face. What shield am I talking about? I could have swore I showed you guys this demonstration in instrumental, so I didn't bring it. The microwave oven. Glorianne, you put your nose right up there so you can smell the popcorn popping.
The grainy thing on the.
I haven't taken instrumental, so lay off.
No, you look at the microwave oven and your nose is right up there next to the
The
glass.
thing in the door. The thing at the door.
The thing in the door, what does it look like?
The grainy
Oh, like a
thing is just-
screen?
It's a screen. A metal, it has to be metal, otherwise it's not going to work, and that's an instrumental thing, right? So, and those little holes have to be what? In that screen, they have to be smaller than the wavelength of
The microwave.
the microwave that thing's generating. Exactly. Okay. How big is a microwave according to this thing, Alyssa? A microwave wavelength. Man, how big is this thing?
What's from like 30 centimeters to 3 millimeters?
Yeah, 3 millimeters. So that means all those little holes are going to be, well, I don't know, they're not 3 millimeters. They're pretty big, right? The little holes are about 3 millimeters or 5 millimeters or so. So the microwaves in the microwave oven are probably more close on the order of centimeter range, right? Okay, so there's a bunch of questions. Oh, we have some symbols that we should get used to. We've got lambda. We've got, here's another symbol, a nu with a tilde on it. And then we've got another one, a nu with no tilde. What were these? You recognize any of them? Lambda's wavelength. I'm going to circle a wavelength on here. What would I circle? Like if I start here, how far would I go to get a wavelength?
The next crest over.
The next crest over. A repeating unit. So you can snip it out and paste it again, again, again. There's a wavelength. Okay, so we got that one. What are the units of wavelength? Yeah, any distance, right? Centimeters, nanometers. What's nano again, Melissa?
I said -10. You say Melissa?
I was looking at Alyssa.
9.
Alyssa, 10 to the negative 9 meters, right? Okay. How about this guy with a tilde on it?
Wave numbers.
Inverse wavelength or wave numbers. Very good. Units of most common, inverse centimeters. 1 over wavelength, right? Remember that? The nu is frequency, yeah. It has units of hertz. There they are. So wavelength is this one, right? Frequency is the bottom one. Okay. So just remember this stuff. Wouldn't that be right? Frequency c over lambda. It all starts really with E equals h nu. Remember doing that stuff? Okay. Emission spectroscopy. We have energy going up. They're gonna show this a lot, and they're gonna write E0 or they're gonna write E1. What are these E0s and E1s doing?
They're doing a lower and higher energy.
Lower and higher energy of what? We're talking about spectroscopy.
State.
The energy states of what? Of the molecule. Of the molecule, right? So you can have term symbols on there. You can do whatever you want, right, to describe these states. But energy is quantized, right, at these microscopic systems. So if I'm going to talk about emission spectroscopy, I'm going to draw a little arrow from where to where, Jeffrey?
An arrow from E0 to E1.
Draw a little arrow from E0 to E1. That's not emission, that's absorption. Whoop. Absorption, right? And then they'll write something like, okay, well, let's do the other one. E0, this is what I was trying to draw, to E1. Emission is going to, little arrow is going to go from where to where, Gloriana? If you want to emit light.
Down.
Down. So what does that mean? That means that emission is, that molecule is right here. It is in its what state? Excited state. And it's going to return to the ground state. And it's going to emit light. Or they'll draw this little thing, right? That emitted a photon. And very often they don't write the E equals h nu. They expect you to recognize that. That energy of that photon is the energy difference, E1 minus E0, right? It's the energy difference. So that frequency, that color of that light, that's it. That's the only color you're going to see. Over here, now it's absorbing it, right? To get to the excited state. It started out in its what state? Ground state. Okay. If my E0s and E1s are the same, is it going to be the exact same color? The exact same energy that's absorbed as emitted? No? If
it's absorbing green, it's emitting red.
The way this is drawn.
Oh.
We'll get things more complicated and do real life scenarios. But the way this is drawn, all we have is two states, a ground state and an excited state. So either, and you get absorption, and then you get emission. Right now we're saying those are our only two choices. That's all we're aware of. Those delta E's, E1 minus E0 is the same for both. So they're both going to be the exact same color, the exact same wavelength. What we're talking about right here. Okay, and Mel, you're talking about the future. Okay. Dispersing element. Again, the big idea here is spectroscopy. So if you want to do spectroscopy, right, you need to get this little frequency there, you need to generate some of that so it will jump from E0 to E1, right? In fact, if you can, well, how do you do that? How do you generate just that light? We can do this pretty good. What kind of radiation is this? Black body emitter. Very, very good. You're taking any object and heating the crud out of it, and it glows. So why they pick tungsten wire? Because then it's nice and bright, and at 9 volts, you can really get it super hot. You just got to keep all the oxygen away. That's why you got the bulb, right? So, but this is going to be all the colors. How do you get just, I don't know, we need red. How do you get just red out of here? You use a, what is this called? Dispersing element. Okay, well, we never use the word dispersing element. We use the word what? Gradient, right? Okay, here we go. So does how does it? There, that doesn't really work too good. Yeah. Yeah, what down here? Ooh, there's a gradient, right? Okay, so okay. Now if you so you have your little, I guess I have to draw this. I'm not very good at drawing. I'm trying to draw a light bulb, right? And then it goes through you get all these different frequencies coming from it, right? It enters a black box. Right? And out comes 1. Maybe I could make one of these red. All right, so somehow I just picked that one. Right? Make sense? So you have a dispersing element in here. This whole black box was called a what? Instrumental people. Start with an M.
Oh,
Monochromator. Yeah. Don't really. It's not. This guy doesn't care, so we don't care either. But the point is dispersing element. Do all of our. So it seems like if you want to do spectroscopy, you need to know what the wavelength is. Otherwise, what's the whole point? You're not going to know what the energy transition is, all that kind of stuff. Hey, by the way, if we're talking about absorption and emission spectroscopy, that's pretty much all in the visible and UV, ultraviolet. Why is that? Because we're talking about electronic transitions. If we're talking about emission and we're talking about absorption spectroscopy, we're really talking about electronic transitions. That all falls in the visible and the ultraviolet. What's an electronic transition? Remember, everything's the interaction between light and matter when it talks about spectroscopy. So when we shown if we wanted molecules to spin faster, well, that's microwave spectroscopy. Well, now we want to do electronic transitions. Ooh, what's going on with the molecule? Something has to change. What changes?
The electron.
The electrons, their distribution. You can call them their orbitals, their electron density, wherever the electrons are at, right? They're clouds, electron clouds. You're changing that kind of stuff. Big energy stuff. These are high energy transitions. Okay? Okay, so talking about absorption emission spectroscopy, we're talking about visible and UV range. If you want to do some spectroscopy, you want to get a certain wavelength out. It's called monochromatic, by the way. Monochromatic, single color, monochromatic output. Okay, so that's one way to do it, dispersing element. But what if you don't have a dispersing element? Well, then you just use a Fourier transform. Okay, I think we're going to have to go on a little field trip, and I can't bring my little camera with me. Let's go show you one, because I took it apart. It's pretty cool, I think. Keys. Okay, we gotta be fast about it though. So, what if you do not have a dispersing element? You use a Fourier transform. All frequencies, same time. That's going to be a lot faster than a UV vis or some other spectrometer. So what happens? Well, you have to have a signal. You have some signal that has variation in intensity and I'd like, usually sometimes, convention is confusing. Like history kind of screws things up, but not really here. They like to, because you remember wave number? I could be talking about any of these, and I'm talking about the same thing. Wave number, wavelength, frequency, it really doesn't matter. But historically speaking, they like to talk about wave number. I like it because it's 1 over distance. It's a distance. So you have this variation in intensity with distance. But think of it this way: you have this signal, and you shine this light, like this table. This table is some kind of gas cell, right? So first I suck all the gas out, and then I shine the light through it. So I get this incident intensity kind of thing. I see what's actually there with nothing in the gas cell, all the background stuff. Okay, we blow a bunch of gas in there, right? Shine the exact same light through. Now certain wavelengths, certain wave numbers, got attenuated a little bit. Depends on which frequencies were being absorbed. Does that make sense so far? Right? So that information is all right here. They call it I. So the intensity varies with wave number because, right, a certain wave number is going to be a little bit attenuated in comparison to where they were in the first place. So it's this ugly signal. And that's all it is just shining something through a gas cell. Bam. Okay. So then what you do is you have to do something mechanical. And get, let's just use their notation, G of omega. So it's the changing intensity. How do you spell intensity? Changing intensity with distance. So you get some plot, G of omega, change of intensity with distance. That's what this figure is. That's this thing. Okay, G of omega. Okay. So, and we saw the mechanical part is that mirror sliding back and forth. Okay, so, I mean, what good is this? And this doesn't even look like anything, right? You've seen this all the time on the NMR. They don't show you this on the, oh yeah, maybe the FTIR does. Doesn't it show you some ugly signal? I don't know, maybe it doesn't. I don't think it does. You don't get to see the intermediate step on the FTIR, but you do on the NMR, the free induction decay, but you don't get to see it on the FTIR. And that's history, I guess. That's just how they make the thing. If you showed it, then people are gonna think, oh, what the heck? What's your machine doing? So no one shows it with FTIR. Then you get it back again. Here's our I of which we wanted in the first place, right? Here's the intensity, and here's our wave number. So what wave numbers were attenuated? Which ones were changed? What is your signal made up of? Different intensities at different wave numbers. That's your spectrum that you're interested in the first place. How do you get it? You have to apply an inverse Fourier transform. Now we're just going backwards, but the idea is still Fourier transform. But technically it's inverse, so that's why I'm writing inverse. So that's how you get your signal back again. So you started out with it, you wanted that, but how do you measure it? You have to get it somehow into our physical domain so you can measure it. So do something mechanical, have something that interacts with that signal with, in this case, with distance is the easiest thing. And then you get how that intensity is changing as you move that distance. You know exactly how far you moved it. You know exactly how you know exactly how far you moved it. You know exactly what the intensity is. That's what this plot is doing. Inverse Fourier transform, and then you're back. Right? I guess that's how I would write it. Ft to the -1 or something. Okay. So what's moving as you get this? What's this x-axis? What's moving with that FTIR? What's the physical thing that's moving and you're changing the, right? The mirror, right? The mirror, right? So it's here. The mirror's here, measures the intensity. The mirror moves a little bit over here, measures the intensity. Moves here, measures the intensity. Moves here, right? So there's a really nice stepping motor in there. You can't even see little dips or anything. It's very smooth. That's probably why it's so expensive. Okay. detector. I think we know what a detector is. Raman spectroscopy. Raman spectroscopy. Okay, if there's a setup of one, they're using a laser sample cell. Looks like most of the laser light just goes straight through, right? But some of it, Raman is all about absorption or scattering. Does anybody know?
Scattering.
It's all about scattering. Raman's all about scattering. So if you have the money, you'd be better off buying a Raman spectrometer than you would a UV vis, because everything scatters light. Well, almost everything. We'll talk about what doesn't. But it's much more universal. But anyway, so if it's going to scatter light, well, I guess you can scatter light. Think of it this way. See if you remember this. Okay. Molecule A, I guess light. Okay. What type of collision is this? For you people in physics? Oh.
Elastic.
What type of collision is this? Oh, you can't even really see it because the lights are off. Elastic, right. So that's one type of scattered radiation. It's going to be elastic, right? So the incoming photons coming in from the laser, does it change frequency? It's elastic. What does elastic mean? This guy's when I'm talking about light, though, I guess, so stick to the idea of light. The energy doesn't change. It's completely elastic collisions. Nothing's lost. So you have this at the beginning, you have this color at the end. It could be red, comes in, it scatters off red. It's an elastic collision, but conceptually it's this. This is so slimy, that's why I brought this paper along. Okay, I got my slimy, dirty, filthy clay here. Red light, the molecule, right? Coming in, right? What type of collision?
Inelastic.
Inelastic. It's inelastic, so this thing is not going to come off as what color? Red. Now this is where it gets weird. You would think it would almost, this red would almost always give its energy to this, right? So what is a lower, what are the energies that are, what are the colors that are lower in energy than red?
Isn't red the lowest visible color?
Red is the lowest visible color. So I guess you could say infrared, right? So you'd think it would almost, if red light is going to undergo this type of scattering, it's going to be scattered off as infrared radiation, right? But there's these, what modes going on in a molecule? Starts with an I? Internal. So that's really what's going on here. These interactions, usually, our brains just like it. Our brains like thinking that this is red light coming in, and then this molecule absorbs some of it, right? So the amplitude increases, and this guy comes off with lower energy. We just like thinking that. But it can go the other way, too, just as easily. These internal modes can enhance this energy. You can take energy from the molecule and add it to the light. So now it wouldn't come off as red anymore. It would come off as what color? Not if you enhance the energy. It has to be a higher energy. Orange, yellow, green, blue, indigo, pick it, right? So it come off as a higher energy. It can go either way. So what do they call those? They call those, oh, they're not both not up here. Stokes is the one that you would expect, right? The scattered radiation, scattered light is lower. Now, can I say lower in frequency, lower in energy? Does that mean the same thing?
Yeah.
It does. So it doesn't matter which one I say. Lower in frequency, lower in energy, same thing. Doesn't matter which one you say. And then there's, I don't have it on here, Anti-Stokes. So you have Stokes scattered radiation and anti-Stokes scattered radiation. Now the scattered light is higher. So if this light, this molecule is undergoing anti-Stokes radiation, this radiation strikes it, it comes off as a higher frequency. Than the incoming photon in the first place. Make sense? Rayleigh radiation. So again, we're talking about scattered light. The interaction between light and matter, so we're talking about Raman spectroscopy, it's just that it's scattering. It's just scattering light. It's not really true absorption. It seems to me there's got to be some kind of interaction or absorption going on because it's with these inelastic collisions. But if incoming light is blue, scattered is blue, that's a what type of collision? That's not inelastic. That's elastic. Well, you're not supposed to say elastic collision. You're supposed to say Rayleigh. That's Rayleigh radiation. That's Rayleigh scattered radiation. It's elastic. Scattered light frequency or energy, same as the incident energy, right? Elastic. Elastic collisions. Okay. Intensities of spectral lines. I brought it. Yeah, I did. I don't know if it's going to work because the darn projector is so bright. Bright. Have you guys seen this? I've shown this to you, right?
We used it.
So you've seen the little individual narrow lines, right? Okay, so we have to do that. Good. So that's what they're talking about here. Spectral lines. Now, a lot of this talk refers to molecular spectroscopy too, but they just want to start out with this. Okay. Now, when they say a line, what are they talking about? A line. Line of what? Color, right? So if we were going to plot this out and say a line spectrum, because they're saying spectral lines, intensities. Intensity would be on which axis probably? The y-axis. So this is intensity. What's on the x-axis? Yeah, it could be wavelength, it could be frequency, whatever you want to do. Usually it's just wavelength. And then if it's just of an atom, okay. And if it's emission, so somehow you had to excite those atoms, and then they emit their light. And it's emitting here only 3 lines, okay, 3 colors. Really narrow, that's why they call them lines. That's why they don't say atomic big fat absorption spectra or anything, right? So lines, because they're really, really narrow. Okay, so how do you describe this stuff? So now it's really confusing because here when you see lines, that's emission. Right? That's how you generate the lines in the first place. But then they jump pages really fast here, and they talk about the Beer-Lambert Law, and they have this IO and this I. They're really not talking about emission here. They're going to be talking about what? Instrumental people, where you have I's and IOs. Yeah, I's are intensities. But how do you go from IO to an I? Absorption. What's IO? IO is... You need a picture. What do you need a picture of? I suppose people have all used cuvettes, right? So draw a little cuvette. Incident is IO, right? Incident intensity. What gets through is what symbol? I. If IO equals I, that just means what?
Absorbing the incident?
If IO equals I, it didn't absorb anything, right? We've got 100% transmittance there. That's how you get 100% transmittance. If I, what got transmitted, is the same, right? That's 1 times 100, then it'd be 1%, 100%, right? Okay. Anyway, so they're talking about absorption now. So what are you absorbing? Well, I guess you have to pick one of these lines. Just pick one. That's the line. And you have this fancy lamp set up, but all you want is that line, all you want is that color. That means we better put a what in front of this before we shine it onto our little sample. Gradient, or the M word, monochromator. Put a big monochromator in here and set the little knob to be whatever this line, this wavelength is. So only that color comes out, and then we'll have our I naught, our incident intensity.
Dr. Smith, you already went over by a minute.
Yeah, but I get to go over by 5 because I
No,
started
you
by
were-
5.
You were 2 minutes late.
So we'll just finish this part. So we have the Beer-Lambert law. I equals I naught 10 to the minus epsilon concentration J. What the heck is that?
L.
L. Okay. What's this L?
The molar absorption coefficient.
That's going to be epsilon. What's L? L is the,
The length of the cuvette?
yeah, the length of the cuvette. They call it the path length. All right. So the longer L is, right, the bigger your absorption is going to be. Right down here is kind of easier to see, right? The bigger L is, the higher your absorption. Okay. Absorbance is the log of I over I naught, which is epsilon. Concentration J, kind of already told you, concentration of whatever your sample is, right? That's doing the absorbing. Okay, so that's its concentration. Sometimes they might just have a little C there. And then epsilon is the ability for that molecule, for that whatever your J is, to absorb at that wavelength that we're shining through in the first place. So all of this should have another subscript on it, a particular wavelength. We're only shining one wavelength through at a time. So absorbance at some wavelength, transmitted intensity, incident intensity. It makes sense to put wavelength subscripts and all that stuff. Not on concentration, not on path length. They don't matter about. Wouldn't make sense to put it on those. Okay. So the Beer-Lambert law, we can actually calculate transmitted intensities, or if you more than likely you measured the transmitted, you've measured the incident, so then you can go off and calculate something like the concentration. If you ran a known through first, so you can know what the epsilon is. Okay. And there's easier ways to get epsilon, like this guy. Get the absorbance at a wavelength, measure the path length divided by concentration, and you'll get the ability for that molecule to absorb at that wavelength. It's never going to change. That's a property like density of that molecule. Okay. So we'll stop there since Al's going to revolt.